Welcome to Ordinary Differential Equations Lesson 24, Eigenvalues and Eigenvectors of a Matrix. The goals of this lesson are to use the characteristic equation of a square matrix to find eigenvalues and their associated eigenvectors. Usually, I guess we say eigenvectors and their associated eigenvalues, but 12 of one, dozen of another. Find the algebraic and geometric multiplicities of an eigenvalue. And note that if a matrix A is an n by n matrix, it can have up to n linearly independent eigenvectors. It might have fewer than n linearly independent eigenvectors. Let's first talk about a square matrix that has an inverse. What can we say about such a matrix? For a square matrix, these statements are equivalent. A is invertible. That means that there is an inverse such that A times A inverse equals the identity matrix. Invertible matrices are also called non-singular matrices. If the matrix is invertible, its determinant turns out to be not zero. Also, for an invertible matrix, the only solution to the matrix equation AX equals the zero vector is X equals 0. And also, once again, for matrices that are invertible, there's only one solution to the matrix equation AX equals B. On the other hand, if a square matrix is not invertible, what can we say about it? Well, let's look at this fact. For a square matrix A, these are equivalent statements. First is that A is not invertible. If a matrix is not invertible, A would also be called a singular matrix. If it's not invertible, its determinant is 0. Remember, we're talking about square matrices, so determinants of matrices, square matrices are defined. The matrix equation AX equals the 0 vector has non-trivial solutions X that are not the 0 vector. And also equivalent to these statements, there are an infinite number of solutions or no solutions to the matrix equation AX equals B. These facts we saw in the previous lesson, so this is basically a review of some things that we're going to be using throughout the rest of this course. We will say that a non-zero vector X is an eigenvector of the matrix A if A times the vector X equals lambda times the vector X for some number lambda. This number lambda is the eigenvalue of A associated with the eigenvector X. Here's what we can say about eigenvalues and eigenvectors. If A has an eigenvalue lambda, which is a number, corresponding to the eigenvector X, then that vector X, that eigenvector, it's a non-zero vector, remember, satisfies AX equals lambda times X. The matrix times X equals this number times X. We could also then say that AX minus lambda X equals 0. This equation can be written as A minus lambda times the identity matrix, that matrix times X equals the 0 vector. And here we have this matrix times the non-zero vector is the 0 vector. That tells us that A minus lambda I is not invertible. But if it's not invertible, the determinant of A minus lambda I must be 0. So we come to the following conclusion. To find the eigenvalues of A, we solve what's called the characteristic equation of A. The determinant of A minus lambda I equals 0, the number 0. The kernel or null space of an n by n matrix A is the following. The kernel of A is a set of vectors x in Rn such that the matrix A times the vector x equals the zero vector. The zero vector is just the column vector n entries, all of which are zeros. Here are a couple properties of the kernel of A. First property, kernel of A is closed under scalar multiplication. That means that if x is a member of the kernel of A, then a scalar c times that vector x is in the kernel of A. Why is that true? Well, let's see. If x is in the kernel of A, then by the definition of the kernel, that means that A times x is the zero vector. So what about c times x? A times the vector c times x is equal to c times the matrix A times x, but A times x is 0. So this is just c times the zero vector, which is the zero vector, and that means that c times x is in the kernel of A. Another property, kernel of A is closed under addition. If x and y are both in the kernel of A, then x plus y is in the kernel of A. Let's see why that's true. If x and y are both in the kernel of A, then A times x is 0, the zero vector, and A times the vector y is the zero vector. Thus, A times the vector x plus y, using properties of matrix multiplication, this is equal to A times x plus A times y. But A times x is the zero vector, A times y is the zero vector. So this equals 0 plus 0, and the sum of two zero vectors is just the zero vector. So we have that the kernel of A is closed under scalar multiplication and also closed under vector addition. The kernel of A also satisfies the other properties of a vector space, if you're familiar with vector spaces, but you don't really need to for this lesson. We can also then state, assuming those other properties hold, that the kernel of A is indeed a vector space. We can define the eigenspace of an n by n matrix A corresponding to an eigenvalue lambda of this matrix A. And let's call that eigenspace, let's denote it by this symbol, E sub lambda. So E sub lambda is defined to be the kernel of A minus lambda times the identity matrix. A is an n by n matrix, and the identity here is the n by n identity matrix. Lambda is a scalar. Remember, we're assuming that lambda is an eigenvalue. So the kernel of A minus lambda I is the set of all x's such that A minus lambda I times x is 0. But that is the same as saying that A times x is lambda times x. So if we look at this, all of the non-zero vectors in E sub lambda are eigenvectors of A corresponding to the eigenvalue lambda. There's one particular vector and only one vector in this eigenspace that is not an eigenvalue. And what is it? Well, if you remember the definition of an eigenvalue, of an eigenvector, it is a non-zero vector satisfying this equation. Well, the zero vector is in this set because A times the zero vector does equal lambda times the zero vector. Zero vector equals zero vector. That's kind of trivial. So what happens then is that every non-zero vector in this set is an eigenvector. So how do we find the eigenvalues and eigenvectors of a square matrix A? First, we find the eigenvalues, lambda, satisfying the characteristic equation. The determinant of A minus lambda I equals 0. We will see that this is just a polynomial equation in the variable lambda, and we can solve these equations in many cases. These will give us the eigenvalues lambda of the matrix A. Then, for each eigenvalue lambda that we found up here, we'll solve the equation A minus lambda I times x equals 0. We want to find an eigenvector x, so we solve this equaling the vector 0, and that will give us the eigenvector x of A, which has the associated eigenvalue lambda. We might find several values of lambda that satisfy this equation up here, and so down here we might find several eigenvectors of A also. We'll see examples of this as we go along. As an example, let's let B be this matrix, and let's find the eigenvalues and associated eigenvectors of B. So what we need to do first is to find the eigenvalues of B by solving the determinant of B minus lambda I equals 0. So first of all, the determinant of B minus lambda I is the determinant of this matrix. It's the same as B up here, except on the main diagonal we're subtracting lambda. If you perform this calculation, so let's say by expansion by minors, you'll find out that this determinant is 1 minus lambda times 3 minus lambda squared. And so the characteristic equation is 1 minus lambda times 3 minus lambda quantity squared equals 0. So the eigenvalues are 1 from here with algebraic multiplicity 1, and lambda equals 3 with multiplicity 2. The multiplicities are the powers that these factors are raised to. You would expect a cubic to have 3 solutions. A cubic equation has 3 solutions, and in this case we have 1, 3, and 3 being the 3 solutions, but 2 of the solutions are the same, 3, with multiplicity 2, since it occurs, since 3 minus lambda has 2 factors, consists of 2 factors in this equation. So here's the matrix B again. Let's see, we had lambda equals 1 was one of the eigenvalues. So let's find the eigenvectors of B associated with lambda equals 1. So what we'll look at is B minus 1 times the identity matrix I, and that's going to be B, except that we subtract 1 from each of the primary diagonal elements. And so here we have a 16, as we have here. 17 minus 1 is 16, minus 27 minus 1 is minus 28. So what we want to do is solve B minus 1 times I, which is this matrix, times a vector equals the 0 vector. So the augmented matrix then for this system of equations from this vector equation, matrix and vector equation, is this. Here's the coefficient matrix right in here, appended or augmented by a column of zeros, because we have 0, 0, 0 as a column on the right hand side. Get the reduced row echelon form of this matrix, and it turns out to be 1, 0, 7/3 0, 0, 1, 1/3 0, and then a row of all zeros. Still talking about lambda equals 1, we're trying to find the eigenvector or eigenvectors. So we got this augmented matrix, and it corresponds to an equivalent system of equations to solve, homogeneous linear equations. Looking at the first row, we see that V1 is a leading variable. Looking at the second row, we see that V2 is a leading variable. looking at row 3, there are no leading variables. So V1 and V2 are leading variables. That leaves V3 as the free variable. So that's what we have here. V3 is a free variable. So let's introduce a parameter. Let's let V3 equal t. Then this first equation gives us V1 plus 7/3 t equals 0. And looking at the second equation, V2 plus 1/3 t equals 0. So that tells us then, by solving these two equations for V1 and V2, that V1, V2, and V3 are minus 7/3 t, minus 1/3 t, and t. Remember, we set V3 equal to t as the free variable, and then we solved for V1 and V2. Okay, and then we can factor out a t from each of these components. This is equal to t times the vector minus 7/3, minus 1/3, and 1. So, as we saw before, all multiples of this eigenvector are also going to be an eigenvector, but not linearly independent of this particular one. There's only one eigenvector in the set of linearly independent eigenvectors for lambda equals 1. So we can say that this set of vectors generated by this one vector forms an eigenspace of dimension 1 for the matrix B. So now let's find the eigenvectors of B corresponding to lambda equals 3. So we're going to solve B minus 3i times an eigenvector equals 0. So here is B minus 3i. We subtracted 3 from each of the primary or main diagonal elements. Instead of 17, 17 minus 27, we have 14, 14 minus 30. So solve this times this vector equals the 0 vector. Once again, to solve that, let's look at the augmented matrix for the corresponding system of equations, augmented by a column of zeros. Look at the reduced row echelon form of this matrix, and it turns out to be this one, 1, 7, 5, 0, and then the second and third rows are all zeros. We are continuing our calculation looking for the eigenvectors of B corresponding to the eigenvalue lambda equals 3. So far we have the reduced row echelon form of our augmented matrix was this. The variables were V1, V2, V3, and then these were the constants on the right-hand side of our system of equations. So V1 is a leading variable. V2 and V3 are free variables. So we can let V2 equal the parameter S, V3 equal a parameter T, and then solve for V1. So from this equation up here, the corresponding equation for this row, V1 plus 7S plus 5T equals 0. So V1 has to be minus 7S minus 5T. So the eigenvector V1, V2, V3 has the following form. V2 we set equal to S, V3 we set equal to T, and from here we found that V1 would have to be minus 7S minus 5T. Now we can write this vector as S times a vector plus T times a vector. If you look at this, S times this vector plus T times this vector does give us this one. S times minus 7 plus T times minus 5 is this stuff. S times 1 plus T times 0 is S, and S times 0 plus T times 1 gives us this third component, T. So what we find then is that we can generate eigenvectors corresponding to lambda equals 3, that eigenvalue, by taking any linear combination of these two vectors, as long as it's a non-zero linear combination. Eigenvectors cannot be zero vectors. So what we find is that the eigenspace of B associated with the eigenvalue lambda equals 3 is of dimension 2. And it is spanned by these two vectors that we found here, and minus 7, 1, 0, minus 5, 0, 1. So this type of calculation is algebraic, basically from linear algebra, but we're going to find that this sort of calculation is going to be very handy in solving systems of linear differential equations later. Eigenvalues have algebraic multiplicities and geometric multiplicities. Sometimes they turn out to be equal, sometimes not. Let's suppose that A is an n by n matrix, and let's let lambda be a root of multiplicity m sub A of the characteristic equation of A. There might be fewer than m sub A linearly independent eigenvectors corresponding to that eigenvalue. M sub A is called the algebraic multiplicity of lambda. On the other hand, the dimension of the kernel of A minus lambda I is called the geometric multiplicity, and I'll call that M sub G of lambda. It's always true that the geometric multiplicity is less than or equal to the algebraic multiplicity. If these two are equal, then we're in a pretty good situation. If these two turn out to be unequal, if the geometric multiplicity is less than the algebraic multiplicity, then we're going to have some trouble, not too much trouble, but a more complicated situation to handle when we get to solving systems of differential equations. Let's solidify these concepts in our mind by looking at an example. Let's let A be this matrix, 3, 1, 0, 0, 3, 1, 0, 0, 7. So the characteristic equation then is the determinant of this matrix equals 0. This is A minus lambda times I. If you look at this matrix, it's pretty easy to find the determinant of it if you're using expansion by minors. Let's expand by minors along this first column. We're going to get 3 minus lambda times the determinant of a submatrix minus 0 times the determinant of another submatrix plus 0 times the determinant of another submatrix. So the only thing that survives in this case is 3 minus lambda times the determinant of this submatrix right here, 3 minus lambda, 1, 0, 7 minus lambda. So this has to equal 0. And this one is 3 minus lambda times 7 minus lambda minus 0. So this determinant is 3 minus lambda times 7 minus lambda, but we have another factor of 3 minus lambda out front. So the characteristic equation is 3 minus lambda squared times 7 minus lambda equals 0. So lambda equals 3 from right here has algebraic multiplicity 2, and lambda equals 7 coming from right here has multiplicity 1. But what about the geometric multiplicities? Let's see. For the matrix A equals this stuff, we saw that the characteristic equation had solutions lambda equals 3 with multiplicity 2 and lambda equals 7 with multiplicity 1. These are the algebraic multiplicities of those eigenvalues. The algebraic multiplicity depends on the characteristic equation. But what can we say about geometric multiplicities? Well, if we look at lambda equals 3 we want to see what eigenvectors it has corresponding to that eigenvalue. So we'll look at a minus 3i times v equals 0. If we take a minus 3i, we'll start with the matrix A up here, subtract 3 from each of the elements on the main diagonal, and so the main diagonal becomes 0, 0, and 4. The other elements stay the way they were. So we have this matrix times v equals 0 for a minus 3iv equals 0. If we get the reduced row echelon form of the augmented matrix for the system of equations, we get this. 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Looking at the first row, we see that v2 is a leading variable. Looking at the second row, we see that v3 is a leading variable. The third row does not give us any leading variables. So v2 and v3 are leading variables, and that leaves v1 to be our free variable. Find the leading variables first, and what's left over are the free variables. So now let's set that free variable v1 equal to the parameter t. So we get v1, v2, and v3 have to be what? Well, v1 has to be t. That's what we set it equal to since it was a free variable. And now look at the equations that we have up here. 0 plus v2 plus 0 equals 0. That forces v2 to be 0. Look at the second equation. 0v1 plus 0v2 plus 1v3 equals 0. That sets v3 equal to 0. So all of the eigenvectors have to look like t, 0, 0, which is t times 1, 0, 0. So we get that all solutions to a minus 3iv equals 0 are multiples of this one vector. This one vector generates the eigenspace corresponding to lambda equals 3. That means that the geometric multiplicity of that eigenvalue, lambda equals 3, the geometric multiplicity is 1. We're still looking at A equals this matrix. We see that it's a 3 by 3 matrix, has 3 rows and 3 columns, but it only had one eigenvector for the eigenvalue lambda equals 3 and one eigenvector for lambda equals 7. So A does not have a set of 3 linearly independent eigenvectors. The biggest set of linearly independent eigenvectors you can have is 2. That tells us that A is not diagonalizable. We cannot find a matrix P such that P inverse AP is a diagonal matrix. So the method that we covered in this lesson for solving x prime equals A times x will not work in this case. What can we do? Well, it turns out that if we look at the equation A minus 3i quantity squared times V equals a 0 vector, this equation does have 2 linearly independent solutions, and those are called generalized eigenvectors of A, corresponding to the eigenvalue lambda equals 3. We will discuss them in a later lesson and see how we can use those to solve this equation x prime equals A times x when A cannot be diagonalized. So stay tuned for further details on that method of solving x prime equals ax. I hope you enjoyed this lesson, and please continue. So, what have we done in this current lesson? We learned to use the characteristic equation of a square matrix to find its eigenvalues and their associated eigenvectors. We defined and found the algebraic and geometric multiplicities of an eigenvalue, and we looked to the future in future lessons, that is, where we will use these techniques to solve this differential equation. The derivative of a vector x with respect to t equals matrix A times x. In this equation, we will think of x as being a vector function of t. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.